will prove the existence and uniqueness of determinant function for any n times n matrix. Alright, so first of all, we consider n equals 1, so it's one-dimensional matrix. Okay, and so the matrix will be just any one-by-one matrix, just like this one, right? Only one entry. And so the determinant of such an entry, so that here, by scaling property, right? So by scaling property here, so we have x times the determinant of 1. But 1 is the identity matrix. So the value is 1 by all x and number 1, right? So it's x for all. So the determinant function one by one matrix is this, and is unique. Okay, so we're done for n equals 1. So we have answered the question for n equals 1. All right. So now we now state our theorem 4.1.2. Actually, it's a theorem stated in section 4.1 of the textbook without any proof. So now we are able to prove it. Okay, so the determinant function dt on the set of all n by n matrices exists unique. Okay, so you will use the fraction. Okay, so now for n equals 1, what we have done. Okay. Okay, I think I have to make a remark. Actually, all right. So the scaling. The scaling property, give us that. So if, right, so this just shows that if I have to make if it exists, all right, should be. This matrix, okay, and I think I have to sample. the function okay, the function satisfy axioms 1, 2, and 3. Right? Because that we ask that if any determinant should satisfy axiom 1, 2, 3. Axiom 1, we call axiom number 1 is that the determinant value of the identity matrix is 1. Okay? And the second axiom says that we have linearity on the first row of the matrix. The third one is that if we exchange two rows, then we have to change the sign of the determinant. Okay? So we have 3 axioms. And it's very easy to see that it says axiom 1 because if x equals 1, then it's 1. If this is 1, then it's 1, of course. Linearity is linear, of course, because you have only one row. So this is the first row, and it has only one attribute. So actually, this is the so-called this is linear function. So it's linear. Exchange row. You have to know rows to exchange. so that it satisfies automatically. Okay. So that's okay. So this is actually this shows the existence of DBT for n equal to 1. Okay? So we have to finish this part. Alright, so now for induction of n, right? So for n equal to 1, we have done. Because we just proved that the determinant function is the determinant function exists and it is in MIP. Okay? For n equal to 1. Good. Alright, and for n equal to k, we assume that determine on the set of all k by k matrices and k times k exists and is unique. Okay? Alright, so we say that it's unique and exists. Now we go to n equal to k plus 1, and we consider an arbitrary k plus 1 times k plus 1 matrix. Alright, so then by cofactor expansion, using, alright, just row 1. Okay, just row 1. We have this formula, right? Row 1. We have ddt A equal to j from 1 to k plus 1, A1j minus 1 1 plus j, determinant of the 1j minor of A. So this is our covector expansion formula using rho 1. So A1j, A11, A12, A13 up to A1, right? K plus 1 are entries in the first row of the matrix. So we have that. Now since M1JA is K times K matrix for all J, so determinant of M1JA is uniquely okay, once again, I have to say we have if exists. Okay, so by we have if okay, so if the determinant function det on the set of all k plus 1 times k plus 1 matrices exists, then they must be like that. Because as I said many times that we have things from at the beginning of the chapter is that to assume that a determinant function exists. Okay? Alright, so since M1JA, alright, is K times K matrix. Alright, for all J, determinant of M1JA is uniquely determinant. So that DETA is uniquely determined. If DET exists. But now we can use this formula, but the function det right? Now, but the function defined is this way by using the formula. Alright, so we define from any such a matrix map to this one, but the function satisfy xm1, so we can check one by one. Okay, we check one by one. So we check dt right? So we check by using this formula. And the expression is on the first row. So dt 1, 0, okay. So now by the first expression, you have 1. There are only 1 entry. Okay? And minus 1, 1 plus 1. Okay, and the determinant of, again, is identity, k times k. Because this entry is A11, okay? And this one is equal to M11 I k plus 1 k plus 1. Because this identity, when you remove the first row and the first column, you get identity matrix. Right? Because this part is an identity matrix. So here, okay, so the minor, so the 1 minor of this k plus 1 by k plus 1 identity matrix is equal to the k by k identity matrix. The other entries are all zeros, so you multiply zeros can be just 0. Okay. And so this is 1, because that by deduction that we have a unique. There exists a unique and determinant function for n equal to k. So this is 1 times 1 times 1 equals 1. Right? So the determinant function of the identity matrix is equal to 1. So this is first satisfies axiom number 1. Okay. Axiom number 2, linearity. So now, the determinant of alpha R1 plus alpha prime R1 prime and R2 extra k plus 1. Right? So the first row is a linear combination of 2 row vectors. Right? So we have determinant of so the first row is alpha say A11, okay, plus alpha prime A11 prime. And alpha A12 plus alpha prime A12 prime. alpha A 1 k plus 1 plus alpha from A 1 k plus 1. Okay, so this is the first row. And we have R2 to R k plus 1. Alright, so this. Now, by the definition of this function, because we have an expansion formula for that. So this is dimension. Alright, so we have alpha A1j plus alpha from A1j prime. That's 1 plus j, and the determinant of A. Determinant of M1j. And here is alpha. Okay? Is that okay? Just plug in the definition of this function by using this formula. Okay? Any questions? Oh. Alright, now I just, because it's sum, right? So I extend to sum. So here I have alpha here. A on j minus 1 plus j, determinant M1j, alpha plus alpha from A plus 1, and plus alpha from A1j prime. Then alpha from 1 from okay. Is that okay? I just split the sum into 2. Now, the minor here, this minor, of the matrix where the first row is just a linear combination of 2 row vectors. This one is equal to the minor of 1j of another matrix. Which one? What is that? 1, 2. Why? Because 1j minor means that we will remove the first row and remove the jth column. But remove the first row means that I will remove the first row too, right? So indeed, you can put arbitrary row vector here without change. Right? This is because we remove the first row to get the minor. Okay. So my purpose is just replace this matrix by this matrix for my purpose. But the reality is that I can replace the first row by any row vector. Okay? This is the reality. But I just choose one for my purpose. Similarly here, my purpose is to replace this minor to M1J. Now I want prime to up to okay, minus. Is that okay? Any questions? Okay, so now we have alpha summation j from 1 to k plus 1, a1j minus 1 plus j, determinant of m1j, here is 1 to k plus 1, plus alpha prime summation j plus 1, k plus 1, a1j prime plus 1 plus j, determinant of m1j, 1 prime to k plus 1. Alright, and now by definition, here, by our definition of, I just erase that. Anyway, so this is determinant of R1, R2, k plus 1, plus alpha prime determinant of R1 prime, R2, k plus 1. Okay, so now, starting from here, the first row is a linear combination of two row vectors. Its determinant value is equal to the same linear combination of the corresponding determinant of the vector here with row R1 and a matrix, and the matrix for the first row is R1 prime. So DT is linear. The first row. Alright, so this is axiom number 2. So it satisfies axiom number 2. Okay. Last one, axiom number 3. All right, so determinant J I so two cases. Let me do it. Case 1. The I and the J, alright, so they are bigger than 1. So determinant of 1 here I, J, K plus 1. Okay, so that summation J from 1 to K plus 1, A1J minus 1 plus J, determinants of M1J, 1, I, J, K plus 1. Now, so this is equal to A1J. Now, if we exchange the I0 and the J0, we will exchange them. Then the minor will exchange the corresponding two rows. Why? Because minor 1J means that the first row is being eliminated, but the I's and the J's row still there, except that the column. Oh, sorry, I shouldn't use J because J has been used. Oh, that's mine. Never mind. I just change to N. Okay. Sorry. All right. The index. All right. Press. Okay. All right. So because M1M, we will remove the first row, but keep the I0 and the J0, the corresponding I0 and J0 here. So that if we exchange them, the minor will also the corresponding two rows will change. So the determinant value will become. We will have to change the sign. Okay, so if we exchange them, so here this is the ith row, this is the jth row. Again, here this is the ith row, and this one is the jth row. So you have to change the sign here. Okay, and so now the first row, right? The A1M is still the entries of the first row. So now we have the minus determinant of R1 J I K plus 1. Alright, so we've done for example 3 in case number 1. If I and j are bigger than 1. So that by the formula, automatically we have to change the sign. Because in here, we have to exchange the sign. For this k times k matrix submatrix. So we have to change the sign here. Alright, so there is only one case left. Okay. In this case. Alright, so the determinants of 1, j, k plus 1. So here this is the jth row. And by our expansion formula, so k plus 1, a1j plus 1 plus j, determinants of j. All right. Oh, sorry. So I think I forgot to change the index to m. Alright, so it's m from 1 to k plus 1. Now, if we exchange the first row and the jth row, okay, if we change them and then to take out the first row, now the okay. So we will remove, because if we exchange Rj with R1, right? And then after that we do we take the minor, then we will remove the whole Rj, because we change them to there. So so what we will do is that by the linearity, all right? So a better way to do so is that I think I have to do I have to do the expansion. Okay. There are two ways to K plus 1 and A1M minus 1. Another determinant. It's a little bit tedious, but let me see, can I have a simpler approach? I think that's fine. Okay, let's see. Before I change them. I have to do something. Okay. I will it's better to illustrate. And this one is A1, A2M, A2K plus 1. And A K plus 1, 1, A K plus 1, M, A K plus 1, K plus 1. Alright, and the minor is that we move. Alright, so we move the first row and the nth column. Okay. So now I will if I exchange them, Okay. Alright. Root 1, k plus 1. And determinant. So I have a to 1, a to m minus 1, a to m plus 1, a to plus 1, and a to 1, a to m minus 1, a to m plus 1, a to k plus 1, a k plus 1, 1, a k plus 1, m minus 1, a k plus 1, m plus 1, a k plus 1, k plus 1. Right. So this one is the k times k matrix. All right. So we have, so this is a k times k matrix. And we already know that the determinant function exists and is unique for any k by k matrix. So we can do the extension. Okay, so now we expand the matrix, the determinant by this row. So this one is the j minus 0 in this matrix. So we have determined, now we have t equal to 1 to k, and a j t. Okay, so here is I have to j from 1 to k plus 1, but j is not equal to m. Okay, and a j s t, so it's j t. Okay, and minus 1, j plus t, and determinants of a smaller dimension. So that so I will say m jt, okay, of m. The original one is 1m of the matrix. 1 j. All right. So this matrix has been is the minor of the original matrix already, and then we get the minor again. So we have 2 layers. 1, 2, 3. All right. So that for example, this is the this column. All right. So we have this column here. Okay. So now we change the order of this part. So now we have a t from 1 to k plus 1, and t not equal to so I have m. Okay. And now so if I exchange them, I will, let's see, choose alright. I have t from 1 to k plus 1 and a j t plus 1 j plus t, okay, summation and from 1 to k plus 1 and a1 m. Okay, great. And determinant of m, j, p, and m, 1m. Alright, 3. Minus the summation. So the minus would be for each m, okay, the minus, and from 1 to k plus 1, and a j m, a1m minus 1. So 1 plus m minus 1 j plus m, and the determinants of j k plus 1. Alright. The reason why we have to subtract another sum is because here in the expansion that we do not have to t to m, because you see the index m has been in here has been removed already, right? The original m's column has been removed already. So that we have only, so in this k by k summation, we have only k matrices, right? 1 to m minus 1 and m plus 1 to k plus 1. So the summation here, because the summation is set from 1 to k plus 1, but we have to eliminate t equal to m. But in here, because we want to extension, so the sum here is t plus from 1 to k plus 1. So that I have to remove 1 corresponding to t equal to m. Okay, so that's t equal to m. This is t, right? Equal to m and m here. Okay, so ajm, aj1m, and the two sign here. Right, the trace is the same. Okay, now this is the. So now we will synthesize again back to alright. So what is MJT? The MJT is that we remove this column. So will be J minus 1, I'm sorry. It will be J minus 1, sorry. Because here is the J minus 1 0. Okay, so now no more errors. Okay. Alright, now for here, for this one, for this one. So and for this one, it is because that with the summation is much more bigger, right? Because that we have k plus 1 entrances. But what we need is only when we remove them. And the this column, we will basically we have to we want to do something that is here. Now I will exchange them. Okay, so now I will move save at 1. So basically I will replace the j minus 1 row by, I will replace them by another matrix. It will be A to 1, A to n minus 1, A to n plus 1, A to k plus 1. And now I will A11, A1 n minus 1, A1 n plus 1, and A1 k plus 1. A k plus 1, 1, A k plus 1. Yeah. N minus 1, A k plus 1, n plus 1. And A k plus 1. Alright, so basically, I will replace this row by the original first row, so that I will change them. Okay, so basically I will exchange them to do, and so now, and because when we remove them, so these two matrices will be the same. Okay, so that it's so in here I have so I have j here and 1 here. Because these two, after taking 2 steps of minors, the k minus 1 times k minus 1 matrix will be the same if we exchange the 2 rows. Okay, so that because we will remove these 2 rows so that they will be the same. Okay, and so we can fill in into that. The entries is included here. Right, so if we remove and this row, this column, so you see that compared with these two, this is also k by k matrix, right? And if we remove the j minus 1 row, so here is the j minus 1 row. If we remove the j minus 1 row and this column, you will see that these two k minus 1 times k minus 1 matrix are the same. Right? So they are the same. So they will have the same determinant. Okay. So that is the idea. So that's why we can now in here we just exchange. So and the R1 doesn't matter. So I just put the first row to Rj, and this is R1 here. So this is from this observation to see that in here I can exchange them. Right? And similarly, I will do that. This is Rj and R1 here. But I have to add one thing, because in here I want to pick out, let's see, so I have to m not equal to t. I think so. Right? So m not equal to t. Because I remove the t, right? This row, so here, and so I will add t from 1 to k plus 1, and a jt minus 1 k plus t, a1 t minus 1 plus t, and the determinant of m j minus 1 t m 1 t and r j r1 r k plus 1. Okay, good. Because I take out one term here, so I have to add back. When I add back, you compare with these two. Except we use t instead of m, they will be the same, right? They are all the same. T and here is m. Sorry, I forgot to put m here. The correction m. So that 8 and the minus, so we can cancel them. Right? Cancel them. And so finally we have this. Alright. Okay? But this is the same, right? So we can go back. Because this identity, we can go back to here. We can go back. So when we go back, so it's the symmetry, right? This one is similar to this one, except the change of the two rows. But there is one thing I have to say is that the minus sign. Where is minus sign? Let's see, where is the minus sign? Oh, okay, it's here. So we do it. Yep, I think this is j minus 1 because I take out j minus 1. So j minus 1 here. So now okay. AJT. So here will be the, okay. 1 plus T summation M from 1 to k plus 1, but M not equal to T, right? And A1M, J minus 1 would be J minus 1 plus M. Okay? Determinant. And J minus 1. So T and M. I think I missed. I have. I have mixed some minus 1, but I can't see it. Alright, let me do it what I have. Minus 1 M and 1 T J 1 J plus 1. This is fine, but this part is correct, but I missed something. Right. The problems here. It depends on the m. So, all right. If t is less than m, then the index will be the same. But if t is greater than m, then the index will move to the left. So the t must reduce by 1. So I have to put them into, okay, it's okay. So it depends on, so this is t if t is less than m, but t minus 1 if t is greater than m. So that because the column index for here, originally this is in the m plus 1 column, but by removing the m's column, this becomes the m's column. So you have to shift a little bit. Okay, and here, again, I have to replace this one. T is less than m, and t minus 1 is t greater than m. So it's not like that. Yeah. All right. And so if I exchange them to here, I have to okay. That's the reason why the minus one is missing. So I have to put minus sign here. If I take them in the other way, so that this comes to minus 1, and for here, I have to m, if m is less than t, and m minus 1 if m is greater than t. Okay, so now I have to have t here, and m, and this, okay, this product is m, if m is less than t, and m minus 1 if m is greater than t. Yeah, so I have to exchange them, and I have to put a minus sign here. Okay, I'm sorry, it is because that. So so now I have, sorry, I have minus sign, okay, and this one plus m, okay, and this one t, no problem, and here I have m if m less than t, m minus 1 if m greater than t. Alright. So that this is minus, as I mentioned, a plus 1, and the a, j, t minus 1 plus t. Okay, and here will be determinants of m 1t j 1 k plus 1. Yeah, okay. So now this expansion is that we take Rj as the first row. Okay, so the AJT will be the entries of the Rj, the first row. And so this is minus determinants of Rj 1 and Rk plus 1. Okay, so we have done. Sorry. So the case number 2 is a little complicated because we have to replace the first row by the Rj. Alright. So when we exchange them, so we have to do the expansion because in here the expansion should be with the Rj because Rj now is in the first row. Okay. And so we finished the proof of the because the existence, right? So the definition by using the cofactor expansion satisfy action 1 and 2 and 3, and so we have done. Yeah. So I'm sorry I haven't thought that. This case is so a little bit tedious. I mean, I have to go deep inside of the expansion. Okay. All right. Okay. So let's just take a few minutes. So we will start the quiz examination of 1125.